In the mid-1930s, a British physicist named Robert Watson Watt was given a strange request: build a death ray. The idea was simple. If you could concentrate enough radio energy, you could destroy an enemy aircraft at a distance. But when Watson Watt ran the numbers, he discovered a hard limit. The power required to damage a plane midair wasn't just impractical, it was physically unrealistic. But buried inside that failure was a different idea. If you couldn't destroy the aircraft, you could still detect it. Because while the energy needed to break a plane was enormous, the energy needed to bounce off its metallic surface and return as an echo was surprisingly small. That single realization didn't create a weapon. It created radar. But there was a problem. The technology of the time, vacuum tubes, was too weak, too inefficient, and too bulky to make this idea truly effective. So for a few years, the concept remained limited. Until 1940, two engineers, John Randall and Harry Boot, working at the University of Birmingham, built a device called the cavity magnetron. It could generate extremely high-power microwaves in a compact form, small enough to fit inside an aircraft. When British officials realized what they had, they did something extraordinary. They secretly transported the technology across the Atlantic to the United States. At the time, they thought they were sharing a better radar component. In reality, they were unlocking an entirely new way of seeing the world. Because once engineers understood what high-frequency electromagnetic waves could do, they realized something profound. Detection wasn't about brute force, it was about precision. Suddenly, radar could move beyond massive fixed installations and become something far more powerful, mobile, accurate, and capable of finding targets in darkness, fog, or open ocean. So how does that actually work? How do you detect something hundreds of kilometers away using a signal so weak it almost doesn't come back? To understand that, you have to stop looking at the radar dish and start looking at the echo. Radar stands for radio detection and ranging. At its core, it's just a game of shout and listen. A transmitter sends out a burst of electromagnetic energy, radio waves traveling at the speed of light. That wave spreads outward, hits an object, and the tiny fraction of it reflects back. If you measure how long that echo takes to return, you know the distance. Simple. But here's the paradox. If only a tiny fraction of the signal comes back, and that signal weakens dramatically over distance, why does radar work at all? To answer that, we need to build the logic step by step. Imagine the transmitter radiating energy equally in all directions. As the wave travels outward, it spreads over the surface of an expanding sphere. That means the energy gets diluted with distance. But radar systems don't behave like light bulbs. They behave like spotlights. Using high-gain antennas, they focus energy into a narrow beam, concentrating power in a specific direction. Now the wave hits a target, say an aircraft. Some portion of that energy is scattered back, depending on the aircraft's shape and material. This is what engineers call the radar cross-section. But the return journey is where things get brutal. That reflected energy doesn't come straight back. It spreads out again over another expanding sphere. So the signal gets diluted twice, once on the way out and once on the way back. Each step quietly drains the signal. And when you combine those losses, you arrive at one of the most punishing relationships in all of engineering. The signal strength doesn't fall off with distance squared. It falls off with distance to the fourth power. That means if a target moves twice as far away, the return signal isn't just weaker, it's 16 times weaker. So now the real question becomes, if the signal is collapsing this aggressively, how do you isolate it from the noise? Because the environment is not empty. When radar waves hit the ground, mountains, buildings, trees, everything reflects energy back. This creates what's known as ground clutter. To early radar systems, this was catastrophic. The Earth itself became a wall of noise, completely masking the signal of an aircraft. So engineers had to find a way to separate motion from stillness. And the solution came from a 19th century insight. When an object moves toward you, it compresses the wave hitting it. When it moves away, it stretches it. This is the Doppler effect. By the 1970s, engineers built pulse Doppler radar, systems that could filter out anything not moving relative to the radar. In other words, they made the radar selectively blind. If something wasn't moving, it didn't exist. And suddenly, targets that were once invisible, low-flying aircraft hidden in terrain, became detectable. Not because the signal was stronger, but because the noise was removed. But even that wasn't enough, because traditional radar had another limitation: speed. Mechanical radar systems physically rotated, sweeping the sky in cycles. That meant delays, it meant blind spots, and it meant moving parts that could fail. So engineers took a different approach. Instead of moving the antenna, they moved the wave. Using thousands of small transmitters arranged in a grid, they could control the timing of each emitted signal with extreme precision. By slightly offsetting when each element fired, they used interference patterns to steer the beam electronically. No motion, just math. This became the Active Electronically Scanned Array, AESA, and it changed everything. Radar was no longer just scanning. It was tracking, mapping, communicating, sometimes all at once. But this power came at a cost. Thousands of active modules generate enormous heat. Managing that thermal load requires complex cooling systems embedded directly into the aircraft. And there's another problem. Every time you transmit, you reveal yourself. A radar system is, in effect, a beacon, a bright signal in an otherwise dark electromagnetic environment. So while you're trying to detect the enemy, you're also making yourself detectable. Which leads to the next evolution. If radar signals are predictable, they can be tracked, analyzed, and jammed. So modern systems are beginning to adapt in real time. This is what's known as cognitive radar. Instead of transmitting a fixed pattern, these systems continuously analyze their environment and modify their behavior, changing frequency, waveform, and timing on the fly. They don't just emit signals, they respond. In a sense, radar is no longer just sensing the environment, it's interacting with it. And this shift changes the nature of detection entirely, because the physics we've discussed, the fourth power loss, Doppler shifts, wave interference, these aren't advantages owned by any one country. They're universal constraints, which means every advanced military system is solving the same problem. How do you see without being seen? From early experiments in British labs to modern phased arrays and adaptive systems, radar has evolved far beyond its original purpose. It started as a failed attempt to build a weapon, but what emerged was something far more powerful. Not the ability to destroy at a distance, but the ability to perceive it.